They are the universe's most magnetic monsters, Magnetars, where a single teaspoon of matter weighs more than a mountain. How can something so small hold such unimaginable power? Tonight we'll explore the strangest stars ever known. If you enjoy cosmic mysteries, please like, subscribe and share, and tell us in the comments, what would you ask a Magnetar if it could speak? Thank you for watching. Now let's begin. The Milky Way extends as a great rotating disk of stars, gas and dark matter, its spiral arms glimmering with regions of ongoing creation and quiet decay. Within this luminous structure there exist pockets of extraordinary activity, dense molecular clouds, where gravity draws matter together to form new stars. These stellar nurseries are not distributed evenly. They cluster along the inner arms close to the galactic center, where gas pressure, turbulence and metallicity are high. From a great distance the galaxy appears calm and balanced, yet inside its crowded zones processes unfold that will one day give rise to the most compact and magnetic objects known. The Magnetar begins its long path here in the same clouds that produce the most massive and short-lived stars. These clouds, made primarily of hydrogen mixed with trace elements, are so large that light takes hundreds of years to cross them. Under their dim interiors, cold dust shields molecules from radiation, allowing gas to condense and fragment. As the density increases, cores collapse and heat, until nuclear fusion ignites, marking the birth of bright hot stars. The most massive among them live brief lives measured in only a few million years. They burn with intense radiation and fierce stellar winds that carve out cavities in the surrounding gas. Each generation enriches the next, seeding heavier elements that influence how future stars form and die. Among the spiral arm star clusters remain as records of these events loose associations in which stars of many sizes share a common origin. In some of these clusters lie the progenitors of Magnetar's stars, perhaps 10 to 30 times the mass of the Sun, their interiors burning so quickly that equilibrium cannot last. The galaxy's pattern of creation and destruction is continuous. Supernova remnants fade while new stars emerge in nearby clouds, linked through cycles of shock waves and chemical dispersal. At greater scale, the Milky Way itself forms part of a larger system orbiting within the local group of galaxies that includes Andromeda and dozens of dwarfs. These interactions stir outer gas and trigger waves of compression that can influence star formation deep inside the spiral arms. The setting is vast and interconnected, but the processes that matter for a single Magnetar begin in volumes no larger than a few light-years across. In such regions, magnetic fields thread through the gas. Though weak at first, these fields can guide the collapse of molecular cores and set the initial conditions that later determine a star's rotation and internal magnetism. Every Magnetar traces its origin to this subtle alignment of motion and field. The galactic environment around the forming star contributes to its fate. In dense clusters, gravitational encounters and radiation pressure can strip outer layers or alter angular momentum. Nearby supernovae inject shock energy into surrounding gas, sometimes compressing material into denser knots that form the next generation of massive stars. Over millions of years, a rhythm develops. Stars are born, evolve and explode, each event enriching and disturbing the medium from which others arise. The Magnetar is one endpoint of this continuum, emerging from conditions that balance mass rotation and magnetic inheritance in a delicate combination. Viewed across the electromagnetic spectrum, the galaxy reveals these cycles in different colors of light. Infrared images show dark clouds glowing faintly with warm dust. Optical telescopes capture glowing nebulae illuminated by newly born stars. X-ray and gamma-ray observatories detect the afterlife's pulsars, supernova remnants and magnetars, whose high-energy emissions pierce the interstellar veil. Against this complex background, magnetars stand out only occasionally, their activity rare and transient. Most of the time they are quiet, hidden among the millions of neutron stars that populate the galactic plane. Their locations often trace the spiral arms following the same pattern as massive star birthplaces. This distribution tells astronomers that magnetars are young by cosmic standards, typically less than 10,000 years old. They still dwell close to the regions where their progenitor stars once burned. Some are found inside or near remnants of supernova explosions, their presence inferred from bursts of X-rays or gamma rays. Others remain unseen until a flare lights up the detectors, marking a sudden transfer of energy from deep within to the surrounding space. The wider galactic structure provides the stage for these events, supplying both the material for their birth and the environment through which their radiation later travels. The magnetic field of the galaxy itself is diffuse, extending over thousands of light years, but within star-forming regions it can concentrate along filaments and shock fronts. Here, turbulence and rotation twist the field lines, amplifying them by orders of magnitude. The same physical laws operate on vastly different scales. What happens in a star-forming cloud echoes in miniature the magneto-hydrodynamic processes that may later unfold within a neutron star's crust and core. The magnetar is thus not an isolated phenomenon, but a natural consequence of the galaxy's long evolution toward complexity. Over billions of years, heavy elements from supernovae have enriched the interstellar medium, altering how stars lose and retain mass. This enrichment affects magnetic field generation and the likelihood of forming extremely compact remnants. In regions rich in metals, strong stellar winds remove angular momentum, influencing the rotation rates at collapse. In others, lower metallicity preserves spin, favoring conditions for stronger field amplification. The variety seen among neutron stars, from radio pulsars to magnetars, reflects these subtle environmental differences imprinted long before the supernova itself. Farther outward, beyond the thin disk, the galactic halo glows faintly with relic stars and dark matter, a quiet background that frames the active regions inside. From this distance, magnetars represent only brief flickers of intense radiation, yet each flicker records an episode in the galaxy's ongoing transformation, where the most massive stars end their short lives by compressing matter into forms of extraordinary density. These objects remind observers that within an otherwise stable spiral system, extreme conditions persist in small hidden corners. The same galaxy that shelters calm planetary systems also hosts the engines of magnetic violence, though their workings unfold in silence across vast stretches of interstellar space. As the narrative draws closer to the birth of a single magnetar, the focus narrows from this wide galactic perspective to one massive star approaching the end of its fuel supply. The environment that shaped it, the gas dust and fields of the Milky Way, has done its work. Now the stage is set for collapse. A massive star begins its life in blinding heat, its surface shining tens of thousands of degrees hotter than that of an ordinary star. Deep inside, the core burns hydrogen into helium through nuclear fusion, releasing radiant energy that pushes outward against gravity's constant pull. This balance defines the star's stability, but for the most massive stars it is a fragile equilibrium sustained only briefly. Their immense luminosity drives powerful stellar winds that peel away outer layers of gas, altering rotation and chemistry over time. Each stage of nuclear fusion occurs more rapidly than the last as the core grows hotter and denser. Hydrogen becomes helium, helium becomes carbon, becomes oxygen, and so on through silicon and sulfur, until finally the core builds iron. At this point, the process changes its nature. Fusion no longer yields energy. Instead, it consumes it, and the core can no longer support the weight pressing down from above. The final collapse begins suddenly in less than a second when the balance between outward radiation and inward gravity fails. Before that moment, the star may appear deceptively stable, its light unbroken, its surface winds slow. Yet within gravity compresses the iron core to the density of atomic nuclei, and the electrons that once supported it through pressure are forced into protons forming neutrons and releasing neutrinos in a flood of energy. The outer layers, finding no support beneath them, rush inward at a significant fraction of the speed of light. When they strike the rebounding core, a shock wave forms. This shock stalls, revives, and ultimately tears the star apart. The visible result is a supernova bright enough to outshine an entire galaxy for days or weeks. It marks the transition from an ordinary stellar life to something new, a neutron star, or under certain conditions a magnetar. The path toward a magnetar depends on factors established long before the explosion. The mass of the progenitor star determines the pressure and temperature in its core, influencing how quickly fuel is consumed and how much angular momentum remains at death. Rotation in turn affects the strength of magnetic fields generated through motion of charged particles in the convecting plasma. In some massive stars, the magnetic field before collapse is already unusually strong, a few thousand times greater than that of the Sun. When the core shrinks to a sphere barely 20 kilometers wide, that field can intensify by many orders of magnitude through magnetic flux conservation, creating the seed of a magnetar's extreme magnetism. In the outer layers, the collapse triggers fusion of lighter elements into heavier ones in a final burst of energy. These layers are expelled into the surrounding space, enriching it with oxygen, silicon, and iron. The remaining compact remnant, just a few solar masses of material compressed into a city-sized object, continues to rotate, often hundreds of times each second. As it spins, it generates electric currents that reinforce the already colossal magnetic field. If the conditions are right, sufficient rotation, strong seed fields, and the right density gradients, the result is a magnetic intensity approaching 10,000 trillion Gauss, the strongest known in the universe. In this newborn state, the magnetar is still obscured by the expanding debris of the supernova. For weeks or months, radiation from radioactive decay dominates the light curve. Gradually, as the ejector thin and cool, the inner core becomes visible through X-rays and gamma rays. Observers on Earth may detect the signature of the new neutron star through the periodic pulsing of its radiation, or through erratic flares that mark the settling of its magnetic structure. The surrounding space, once filled with stellar plasma, is reshaped by this compact object into a new environment governed by magnetism rather than fusion. The transition from massive star to neutron star represents one of the most violent transformations known. Inside the collapsing core, matter experiences pressures billions of times greater than those found inside ordinary atomic nuclei. The result is a sea of neutrons packed so tightly that they behave collectively as a quantum fluid. The entire object is smaller than a large city but contains more mass than the Sun. Its surface gravity is so strong that a particle dropped from a height of 1 meter would strike the crust at nearly half the speed of light. Such conditions alter the familiar rules of physics, requiring general relativity to describe their structure. For most neutron stars, magnetic fields reach 1 trillion Gauss, still enormous but stable. For magnetars, the amplification process pushes beyond this limit, creating stresses that can reshape the crust and even affect the surrounding space. Yet in its earliest moments, the newborn magnetar is turbulent. Its internal fields twist and reconnect, converting magnetic energy into heat. This excess heat drives strong neutrino emission, which cools the star rapidly in the first few minutes after birth. Over time, the outer crust solidifies while the interior remains fluid, allowing differential motion between layers. These motions sustain electric currents that preserve the field even as rotation slows and the core cools. Meanwhile, the expelled debris of the parent star expands into the interstellar medium. This supernova remnant spreads heavy elements across space, enriching nearby molecular clouds that will one day form new generations of stars and planets. At the remnant's center, the Magnetar continues to release bursts of radiation and charged particles. Its rotation may drive a pulsar wind nebula, an expanding bubble of relativistic plasma glowing faintly in X-rays. As the shock waves slow, the nebula merges with the interstellar background, leaving behind only a faint shell visible through radio telescopes. For the galaxy, each such event is a renewal, a mechanism through which material cycles from one form to another. For the Magnetar, it is the beginning of a long isolation. Though small and silent by cosmic standards, its magnetic presence extends thousands of kilometers into space, shaping any matter that approaches. The process that led to this outcome is universal energy. Stored in nuclear binding gives way to energy stored in fields. From luminous star to dense remnant, the transformation converts one type of equilibrium into another, where pressure, rotation, and magnetism replace the thermal radiation of youth. As the shock from the supernova fades and the nebula disperses, the newborn Magnetar enters a quieter stage, invisible in ordinary light, but still active in high energy bands. Its existence now depends not on fusion, but on the slow decay of its magnetic energy. That energy will drive outburst crustal shifts and radiative storms for thousands of years to come. The once bright star has condensed all its mass and momentum into a sphere of relentless gravity and tension, marking the threshold between the visible stellar life cycle and the hidden physics of ultra-dense matter. In the heart of the collapsing star, gravity reaches such intensity that atomic structure itself disintegrates. The iron core, no longer able to resist compression, collapses inward, until protons and electrons combine into neutrons, releasing a burst of neutrinos that carry away a vast amount of energy. This flood of neutrinos moving outward in all directions transfers momentum to the stalled shock wave and reignites its expansion. Within moments, the star's outer layers are hurled into space while the inner core halts its contraction and rebounds slightly, settling into a dense, compact sphere. This is the birth of a neutron star. The transition happens so rapidly that the entire event lasts only a few seconds, yet its consequences endure for millions of years. The newborn object glows faintly in neutrinos and X-rays, though no visible light escapes from its surface. At this stage, the core temperature exceeds 1 trillion degrees Celsius hotter than any ordinary process in the universe. Matter is compressed to densities far beyond those of atomic nuclei, creating a new phase of existence where individual particles merge into a collective fluid. The surface, though briefly molten, begins to solidify within minutes, as heat diffuses outward and radiates away. The magnetic field amplified during the collapse threads, through every layer anchoring charged particles in rigid paths and shaping the space around the star. Rotation inherited from the progenitor ensures that this field generates a powerful electric potential driving currents that maintain the structure of the magnetosphere even before it fully forms. For a short time, the newborn neutron star experiences a chaotic state. Convection and differential rotation twist the magnetic lines, creating a dynamo effect that amplifies the field further. Inside, superheated neutrons and protons move in turbulent flows, while neutrinos stream outward through the dense medium, cooling it rapidly. In the most extreme cases, this dynamo mechanism pushes the magnetic field strength to levels exceeding 10,000 trillion Gauss, transforming the ordinary neutron star into a magnetar. The distinction arises from the speed of rotation and the conditions during this fleeting phase of turbulence. If the core spins fast enough, perhaps once every few milliseconds, the magnetic amplification can proceed efficiently before differential motion ceases. As the temperature falls, viscosity increases and the motion slows, freezing the field into place. From that point on, the magnetar's extraordinary magnetism becomes permanent, embedded in its structure like a frozen storm. The early minutes of the neutron star's life define its later character. If the magnetic field is moderate, the object cools into a conventional pulsar emitting steady beams of radio waves. If the field is extreme, the stored energy begins to distort the outer layers, introducing tension that will later manifest as quakes and bursts. Around the compact core, the shock from the supernova expands outward at thousands of kilometers per second, sweeping up interstellar gas and dust. Inside this expanding shell, the magnetar continues to spin, releasing magnetic and rotational energy into its surroundings. The outflow of charged particles forms a bubble of relativistic plasma, a nebula that glows in X-rays and radio light. Over time, this bubble pushes against the inner walls of the supernova remnant, reshaping it into a faintly luminous cavity. The energy transfer between the newborn star and its environment defines the next stage of evolution. Within the neutron star, matter behaves unlike any substance found elsewhere. The outer layers consist of a lattice of atomic nuclei embedded in a sea of electrons, forming an elastic crust. Beneath it lies a region where neutrons begin to drip out of nuclei, creating a mixture of free and bound particles. Deeper still, pressure forces neutrons into a superfluid state, allowing them to flow without resistance. The interplay between these layers determines how the star cools and how its magnetic field evolves. As the crust solidifies, it locks in the field lines that pass through it, anchoring them in rigid geometry. But beneath this crust fluid, motion continues, slowly rearranging the magnetic stresses that will one day crack the surface. The energy radiated during these first days is immense. Neutrinos remain the dominant coolant, escaping directly through the dense matter. Their production continues until the temperature drops below about 10 billion degrees Celsius, after which photon emission becomes the main form of energy loss. The luminosity falls steadily, and the star fades from a brilliant but invisible source to a faint, persistent emitter of X-rays. Observers on Earth would detect only a point-like beacon if the distance was small enough, yet most remain hidden behind layers of dust and gas in the galactic plane. The star's magnetic poles, regions of concentrated flux, begin to focus the outflow of charged particles into narrow beams. These beams, sweeping across space as the star rotates, create the pulsations characteristic of neutron stars. In magnetars, however, the field is so strong that the emission becomes erratic. Magnetic reconnection events release sudden bursts of energy, briefly illuminating the surrounding space in high-energy light. Even in this early stage, such activity may occur, signaling the magnetar's presence through sporadic flares. The surrounding debris, still dense and opaque, absorbs much of this radiation, converting it into heat that glows faintly in the infrared. As weeks pass, the outer layers of ejecta cool and expand. The remnant's light curve declines and radioactive isotopes formed during the explosion decay, releasing gamma rays that sustain a lingering glow. Deep inside, the neutron star continues to settle. Its rotation slows slightly as magnetic braking extracts angular momentum, sending energy outward into the magnetosphere. The magnetic axis and rotation axis may not align, creating a wobble that modulates emission patterns. This misalignment contributes to the distinctive timing irregularities later observed in Magnetars' sudden jumps or glitches in their rotation rate caused by the complex coupling between crust and core. Over the first 1,000 years, the Magnetar will radiate away much of its initial heat. The surface temperature stabilizes at around 10 million degrees Celsius, still bright in X-rays but far cooler than at birth. Around it, the expanding supernova remnant disperses, enriching the interstellar medium with the elements forged in the explosion. The Magnetar remains at the center, a solitary sphere of compressed matter, encased in an invisible cage of magnetic energy. Every property it now possesses, rotation, field strength, and internal structure, was determined during the brief moments of its creation. The collapse has ended, but its consequences continue in silence. From this point onward, the story becomes one of gradual change, cooling field decay, and the slow emergence of the processes that will one day produce bursts and flares visible across the galaxy. For now, the newborn neutron star, still glowing faintly with residual heat, turns steadily within its expanding cradle of gas and dust, marking the universe's transition from violent motion to quiet persistence. In the seconds after formation, the newborn neutron star is a sphere of extraordinary turbulence. Deep within, layers of fluid rotate at different speeds, generating shear and convection that twist the embedded magnetic field into complex loops. The electric currents produced by this motion form a dynamo, converting rotational energy into magnetic energy. Within moments, the field strength increases to unimaginable levels, thousands of times stronger than that of an ordinary pulsar. In this brief window, magnetism becomes the dominant force in the young star's evolution, surpassing gravity and pressure in shaping its outer layers and the surrounding space. The process unfolds silently, invisible to any observer, but its effects define what follows for tens of thousands of years. Magnetic flux conservation ensures that as the stellar core contracts from thousands of kilometers to a radius of about 20 kilometers, the magnetic field intensifies proportionally. Yet this geometric concentration alone cannot account for the extreme values seen in magnetars. The additional amplification arises from fluid motion inside the proto-neutron star, where hot ionized matter conducts electricity with near-perfect efficiency. Convection driven by neutrino cooling and rapid rotation sustain a dynamo similar in principle to those operating in planets and ordinary stars, though here it is vastly stronger. The outcome is a magnetic field approaching 10,000 trillion Gauss, sufficient to distort atomic structure and influence the opacity of matter itself. Under such conditions, even quantum processes behave differently. Electrons occupy discrete energy levels aligned along field lines, and photons interact with the magnetic field, splitting or merging in ways impossible elsewhere. The star becomes a laboratory for the strongest natural magnetism known. Once the dynamo subsides and the crust solidifies, the magnetic configuration freezes into a tangled arrangement of toroidal and poloidal components. The external field appears dipolar like that of a bar magnet, but inside the geometry is far more intricate. Stresses accumulate where twisted loops of magnetic flux meet the rigid crust, storing enormous amounts of potential energy. These stresses will eventually give rise to the crustal fractures and bursts that distinguish magnetars from all other neutron stars. For now, the field stabilizes, holding the newly formed object in a state of dynamic tension. The influence of magnetism extends far beyond the star's surface. Charged particles trapped by the field form a magnetosphere, an invisible cage of plasma that co-rotates with the star. Electric fields generated by the rotating magnet deform the surrounding space, accelerating particles along magnetic lines to near light speed. These particles emit synchrotron radiation, releasing energy across a wide spectrum from radio waves to gamma rays. In ordinary pulsars, this process produces regular beams of radio emission. In magnetars, the intensity of the field alters the geometry of the emission zones, often suppressing coherent radio pulses and enhancing higher energy radiation. The magnetic field also affects the star's structure. The pressure associated with such immense magnetism is anisotropic. It acts more strongly along some directions than others, slightly deforming the star's shape. This distortion can in principle produce gravitational waves. As the star spins, such signals remain below current detection thresholds. Internally, magnetic tension couples the crust and core, modifying how the star spins down over time. The immense magnetic torque extracts rotational energy efficiently, causing the rotation period to lengthen within a few thousand years. A newly born magnetar might rotate dozens of times each second, but within a relatively short period it slows to 1 or 2 rotations per second, trading spin for heat and magnetic radiation. Observers studying the timing of known magnetars see this rapid spin down as one of their defining features. During the early life of the star, the magnetic field also governs how it interacts with the surrounding supernova remnant. The outflowing magnetic energy drives a shock into the expanding debris, creating a magnetar wind nebula. This nebula, filled with relativistic particles spiraling along field lines, glows in X-rays and soft gamma rays. Over decades it grows in size while the magnetar at its center cools and dims. The interplay between magnetic and kinetic energy shapes the remnant's morphology, carving out cavities and filaments visible through sensitive telescopes. Within the magnetar itself, magnetic diffusion continues at an extremely slow rate. Currents in the crust rearrange the field gradually, while motions in the superfluid core redistribute magnetic flux tubes. The balance between these processes determines how the field evolves. Some theories suggest that part of the magnetic energy migrates from the core to the crust, where it can be released in bursts. Others propose that twisting of the external field stores energy that occasionally reconnects, producing sudden flares. Regardless of mechanism, the root cause lies in the enormous field created at birth. It is this field that defines the magnetar's later behavior, its quakes, bursts, and gradual decay. As the star cools and stabilizes, magnetism remains its principal reservoir of power. Without fusion or significant accretion, the only long-term energy source available is magnetic stress. Over thousands of years, the decay of the field releases heat that maintains surface temperatures far higher than those of ordinary neutron stars of similar age. X-ray observations confirm this persistent warmth, suggesting continuous internal heating driven by the slow unwinding of magnetic configurations. The surrounding space becomes an environment of high-energy particles and radiation extending far beyond the visible star. On a larger scale, magnetars contribute to the overall magnetic architecture of the galaxy. Each outburst injects charged particles and magnetic flux into the interstellar medium, influencing the structure of nearby clouds. Though individual magnetars are rare, their cumulative impact over millions of years may help sustain the diffuse galactic field observed today. Their magnetic energy, once confined to a stellar core, becomes part of the cosmic background, linking the life cycles of stars across vast distances. The concept of magnetism taking over marks a turning point in stellar physics. No other known process compresses energy so efficiently into such a small volume. In the magnetar, the interplay of rotation, convection, and field amplification creates a regime where matter and magnetism are inseparable. The star's interior behaves as a single coherent entity, governed by the laws of quantum mechanics and general relativity simultaneously. Every later stage, the bursts, the slow cooling, the eventual quieting, will trace back to this brief intense episode when magnetism gained dominance. As the Magnetars' early turbulence subsides and the field stabilizes the surrounding supernova, Remnant continues to expand, thinning into the interstellar background. The newborn star, now defined by its magnetic personality, rotates more slowly, emits faint X-rays, and waits in silence for the next disturbance to release its stored energy. The era of formation has ended. The era of magnetism has begun. When a massive star explodes, it does not vanish quietly, but leaves behind a shell of debris expanding outward through space. This supernova remnant forms a visible record of the explosion that created the Magnetar, a slowly fading monument to the violence of stellar death. In its earliest hours, the remnant is a sphere of plasma moving outward at thousands of kilometers per second, glowing in high-energy radiation. The shock wave sweeps up surrounding interstellar gas, compressing and heating it until it shines in X-rays and radio waves. Within this chaotic environment, the Magnetar sits at the center, invisible to ordinary light but exerting influence across the entire remnant through its magnetic field and energetic outflows. Over time, the expanding shell cools and slows as it interacts with the interstellar medium. The interior remains hot and rarefied, filled with particles accelerated to extreme energies. In this cavity, the Magnetar's own winds carve smaller structures, bubbles and filaments that twist in response to its magnetic pulses. The interplay between the outward-moving supernova material and the inward magnetic stresses defines the remnant's evolution during its first few thousand years. Observations of remnants such as KES 73 and CTB 109 reveal this dynamic relationship. Faint rings and arcs mark places where the Magnetar's magnetosphere interacts with surrounding gas, while brighter filaments trace shock fronts still radiating away the energy of the explosion. The density and composition of the local interstellar medium play a crucial role. In regions rich in molecular gas, the shock front encounters resistance, creating ripples and instabilities that distort the symmetry of the remnant. The hot plasma within these zones emits X-rays that carry signatures of elements forged in the original star oxygen silicon iron. Each spectrum is a record of the nuclear processes that took place before and during the explosion. Over thousands of years, these elements will disperse into the galaxy, contributing to the chemical enrichment that makes future planets and life possible. The Magnetar itself remains embedded within this luminous cloud, its radiation shaping the plasma around it. The magnetic field, extending far beyond the star's surface, interacts with charged particles in the expanding gas, guiding their motion and influencing their distribution. As the field lines stretch and reconnect, they inject bursts of energy into the surrounding material, producing faint transient flares detectable in X-rays and gamma rays. Although small compared to the overall size of the remnant, these magnetar-driven events can momentarily dominate its energy output. In the early centuries after the explosion, the Magnetar may power a nebula similar to those surrounding young pulsars. However, because of the immense magnetic field, the energy flow is more erratic, governed by sudden releases of stored tension, rather than steady rotational emission. These Magnetar wind nebulae glow softly in X-rays, their brightness fading as the field decays and the spin slows. Around the nebula's edges, the interface between expanding ejecta and interstellar gas creates complex structures of compressed dust and ionized atoms. Through optical telescopes, such remnants appear as delicate filaments or diffuse rings, faint traces of the star's outer layers, long since detached from the core. The interaction between the supernova shock and nearby molecular clouds can trigger new star formation. As the shock wave compresses cold gas, it seeds the birth of new stars in the same region where one has just died. Thus, the end of a massive star can set in motion the creation of others, perpetuating the galactic cycle of birth and death. The Magnetar, now a dense and silent remnant, becomes part of a chain of renewal stretching across millions of years. In radio images, the remnants often show asymmetries, one side brighter or more extended than the other. These irregularities reflect both the uneven density of the surrounding gas and the directional nature of the explosion itself. Jets of material may have been ejected during the collapse, altering the shape of the expanding shell. Embedded within this asymmetry, the Magnetar continues to emit bursts and flares that further disturb the surrounding medium. Each flare releases energy equivalent to billions of years of solar output, though lasting only fractions of a second. The radiation propagates through the remnant, heating dust grains and altering the ionization balance of the gas. Over time, these events may leave faint imprints, localized regions of higher temperature, or enhanced emission visible in X-ray images. As the remnant expands, its internal pressure decreases. After roughly 10,000 years, the shockwave slows to a few hundred kilometers per second, and the gas temperature drops below 1,000,000 degrees. The structure begins to merge with the ambient interstellar medium, becoming a faint diffuse cloud. By this time, the Magnetar's active outbursts may have subsided, leaving behind a cooling neutron star spinning slowly amid the fading echoes of its origin. Yet traces of its influence remain. Magnetic fields injected into the surrounding gas can persist for millions of years, shaping how future clouds collapse and how cosmic rays propagate through space. Even after the remnant has dispersed, the memory of the explosion lingers in the subtle magnetization of the region. From a distance, such remnants appear as quiet filamentary arcs, ghostly bubbles marking places where stars once lived and died. The light they emit travels for thousands of years before reaching Earth, carrying with it the story of transformation from stellar life to compact object. In some cases, astronomers can still detect the faint X-ray point source at the center, the Magnetar itself spinning with clock-like regularity, or flickering unpredictably in high-energy bursts. Each detection provides a window into the aftermath of collapse, and the continuing interaction between the neutron star and its environment. Surrounding clouds of molecular gas may glow faintly in infrared light, warmed by the residual energy of the explosion. Dust grains absorb ultraviolet radiation and re-radiate it at longer wavelengths, producing the soft background glow observed around some Magnetar remnants. Over millennia, this energy dissipates into the galactic background, leaving behind enriched gas, ready to participate in the next generation of star formation. The Magnetar remains at the center of this ongoing exchange between destruction and creation, a stable core within a field of slow transformation. Its existence connects the microscopic physics of nuclear matter to the grand cycles of the galaxy. The remnant around it serves as both cradle and shroud, a reminder that the most extreme objects in the cosmos are born not from chaos, but from the natural sequence of stellar evolution. As the outer shells fade and the Magnetar's immediate surroundings settle into equilibrium, the focus narrows once more to the compact star itself. Within its invisible magnetic cocoon, deeper processes begin to dominate those that unfold, not in the surrounding gas, but in the space of the field lines that extend outward into the vacuum. The next stage of the journey turns from matter to magnetism, from the residue of explosion to the living architecture of energy that encases the star. Long after the initial explosion fades from view, the Magnetar remains detectable only through the light and radiation it emits. Because its surface is small and its visible brightness faint, Astronomers rely on observations across the electromagnetic spectrum to reveal its presence. Each band radio-infrared, optical X-ray and gamma-ray offers a different window into the processes unfolding within and around the star. Together they form a composite picture of an object that cannot be seen directly, but whose energy leaves a distinct signature across space. The earliest clues to the existence of magnetars came from high-energy observations. Detectors orbiting Earth in the late 20th century recorded short bursts of gamma rays that did not match known supernova or pulsars. These events were brief, lasting less than a second, yet astonishingly powerful. They became known as soft gamma repeaters, sources that emitted multiple bursts over time from the same location in the sky. Later, sensitive X-ray telescopes revealed another group of objects, anomalous X-ray pulsars that shared similar properties but appeared as persistent, slowly pulsing X-ray sources. Both types displayed rotation periods of several seconds, much longer than those of ordinary pulsars, and both showed signs of extremely strong magnetic fields. Gradually, astronomers realized they were observing the same underlying phenomenon, magnetars at different stages of activity. High-energy instruments aboard satellites such as Chandra, XMM Newton and Fermi now monitor these objects, routinely recording their spectral characteristics and timing behavior. In X-rays, a magnetar's emission often follows a two-component pattern, a steady thermal glow from the surface and a variable non-thermal tail from the magnetosphere. The thermal emission reveals surface temperatures of several million degrees Celsius, consistent with internal heating from magnetic decay. The non-thermal component arises when charged particles accelerated along magnetic field lines scatter photons to higher energies. During bursts or flares, the X-ray flux can increase by orders of magnitude, briefly making the source one of the brightest in the sky. The spectra recorded during these events carry information about the star's surface composition, magnetic field geometry, and the processes that release stored energy. Gamma-ray observations capture the most extreme moments. In rare instances, magnetars produce giant flares so intense that they can be detected from other galaxies. The initial spike, lasting less than a second, is followed by a longer tail modulated by the star's rotation. The energy released in such an event equals that of the Sun emitted over hundreds of thousands of years. These flares provide insight into how magnetic reconnection and crustal fractures occur, though the mechanisms remain partly uncertain. The frequency of such events is low, perhaps once every few decades for any given magnetar, but the signatures they leave behind help astronomers identify new candidates, even when no flare is presently active. At lower energies, optical and infrared observations reveal the surroundings rather than the star itself. The expanding supernova remnant glows faintly as dust absorbs high-energy photons and re-radiates them at longer wavelengths. In some cases, infrared instruments detect faint echoes, light reflected from dust clouds illuminated by past flares. These echoes act as time capsules, allowing scientists to reconstruct the history of magnetar outbursts long after they occurred. Optical telescopes occasionally pick up faint counterparts, usually from associated nebulae or nearby stars used to locate the magnetar's position. Because interstellar dust heavily obscures most magnetars, these detections remain rare. Radio observations contribute a different perspective. For many years, magnetars were thought to be radio-silent, their magnetic fields too strong to support the coherent emission mechanisms seen in pulsars. However, a few exceptions have been found showing intermittent radio pulses that appear and disappear in concert with changes in X-ray brightness. This connection between magnetospheric activity and radio emission offers clues to how plasma density and magnetic geometry evolve. when active radiomagnetars emit pulses that vary dramatically from one rotation to the next, reflecting the unstable conditions in their magnetospheres. Timing measurements in this band allow precise determination of spin period and its rate of change, key parameters that reveal the strength of the magnetic torque slowing the star. Across all these wavelengths, timing provides one of the most powerful tools for studying magnetars. Small irregularities in the rotation rate glitches indicate shifts in the interior, where the superfluid core and solid crust exchange angular momentum. These events often coincide with bursts in X-rays or gamma rays, suggesting that internal stresses and external activity are linked. Long-term monitoring shows that magnetars slow down more rapidly than ordinary pulsars, consistent with their stronger magnetic fields. The combination of spectral, temporal, and polarization data helps scientists infer the star's magnetic configuration, even though no image can resolve its tiny surface. Polarimetry. The study of light's orientation offers an additional diagnostic. In extreme magnetic fields, the vacuum itself becomes birefringent, meaning it affects different polarizations of light differently. Measuring this effect allows astronomers to test predictions of quantum electrodynamics under conditions impossible to reproduce on Earth. Upcoming missions aim to observe this subtle signature, which would confirm the influence of the magnetic field on photon propagation near the star. Observations across multiple bands also reveal how magnetars evolve over time. Young magnetars still warm from formation show strong thermal emission and frequent bursts. Older ones emit primarily non-thermal X-rays powered by residual magnetic decay. Some eventually transition into quieter neutron stars indistinguishable from ordinary pulsars except for their slow spin. By combining data from different observatories, researchers can trace the life cycle of a magnetar from its active youth to its gradual fading. Each detection provides a snapshot of magnetic and thermal evolution, offering a glimpse into processes that unfold over millennia. Observing a magnetar is as much an exercise in patience as in technology. The events of interest, bursts, flares, and glitches occur unpredictably separated by long intervals of calm. Telescopes must monitor hundreds of potential sources continuously to catch these moments. When a flare occurs, rapid coordination among observatories allows the full electromagnetic spectrum to be covered simultaneously, from gamma rays to radio. These coordinated campaigns have revealed that energy released in one band often appears in others, linking surface and magnetospheric processes into a single chain of events. Through decades of observation, magnetars have shifted from obscure curiosities to key probes of extreme physics. Their emissions test theories of matter under intense pressure, magnetic fields, and gravity. By comparing observations across wavelengths, scientists build models that connect the star's internal state to its observable behavior. The calm periods are as important as the outbursts, for they show how the magnetic energy gradually relaxes between episodes of stress. In this way, the study of magnetars extends beyond astronomy into fundamental physics, revealing how nature behaves when forces reach their limits. As technology advances, new instruments continue to refine this picture, each photon collected from these distant stars carrying with it information about conditions that cannot be replicated anywhere else. Through this quiet light filtered through cosmic dust and shaped by magnetic tension, the universe allows a distant view into the realm where matter and field are one. Surrounding every magnetar is an invisible yet intricate structure of magnetic lines and charged particles known as the magnetosphere. It extends outward for thousands of kilometers, a vast region where space is dominated not by gravity, but by the magnetic field's geometry. Within this zone, charged particles are forced to move along curved magnetic lines, tracing invisible paths that loop from one hemisphere of the star to the other. The magnetosphere forms the interface between the solid neutron star and the surrounding vacuum, serving as the stage on which much of a magnetar's observable behavior unfolds. Its architecture is shaped by the star's magnetic strength rotation and the slow twisting of the field over time. Close to the surface, the field remains nearly dipolar, resembling that of a bar magnet with north and south poles. But as the distance increases, the configuration becomes complex. Twisted field lines sheared by differential motion in the crust inflate outward and store energy in their tension. When the strain becomes too great, the lines reconnect and release their energy suddenly in the form of bursts or flares. The magnetosphere thus acts as both a storage system and a release mechanism for magnetic power. Its dynamics govern the timing and intensity of the radiation that reaches Earth. The plasma populating this region originates from the star's surface. Strong electric fields near the magnetic poles rip electrons and ions from the crust, accelerating them along field lines at relativistic speeds. These particles emit synchrotron and curvature radiation, producing the continuous X-ray and gamma-ray glow associated with active magnetars. The density of plasma is not uniform. Near the poles, open field lines allow particles to escape into space, forming outflows that carry away rotational energy. Near the equator, closed loops trap plasma, creating regions of higher density and complex current systems. These zones interact through wave propagation and reconnection, leading to oscillations and sporadic bursts. The balance between open and closed field lines determines how efficiently the magnetar spins down. As the magnetic torque acts on the star angular momentum, transfers outward through the magnetosphere, gradually lengthening the rotation period. Theoretical models divide the magnetosphere into three main regions. The inner zone within a few stellar radii is tightly coupled to the crust. Here the field is frozen into the star and moves as one with its rotation. The middle zone, extending to several hundred kilometers, hosts twisted lines and dense plasma currents that store magnetic energy. The outer zone, reaching up to the light cylinder, where co-rotation would require the speed of light, forms the boundary between magnetic control and open space. Beyond this limit, field lines cannot remain attached to the star and instead spiral outward, carrying electric currents into the interstellar medium. The light cylinder defines the outer horizon of the magnetosphere, marking where magnetic dominance yields to the vacuum. Within these zones, energy transfer occurs through waves and instabilities. Alpha waves, oscillations of magnetic tension, through plasma propagate along field lines linking the crust to distant regions. When these waves encounter areas of reconnection, they can trigger localized heating and particle acceleration. Such interactions are thought to power the smaller bursts observed between larger flares. During a major reconfiguration, the entire outer magnetosphere may realign, releasing enormous energy in seconds. The same process occurs in the Sun's corona, though, on a far smaller scale. In magnetars, the fields involved are so strong that even small adjustments produce energy releases detectable across the galaxy. The magnetosphere's shape is not static. As the internal magnetic field of the star evolves, it transmits stress to the surface, slowly twisting the outer lines. Over years, this twist can build until the magnetosphere becomes globally distorted. When the tension exceeds a critical threshold, it relaxes, suddenly emitting X-rays and gamma rays and producing temporary changes in the star's rotation rate. Afterward, the structure gradually returns to a simpler configuration, beginning another cycle of build-up and release. This pattern underlies much of the irregular activity that defines magnetars. Observations show that following a large flare, the X-ray brightness often decays exponentially over months or years, consistent with the untwisting of the external field and the cooling of the heated surface. The magnetosphere also shapes how radiation escapes from the star. Photons emitted from the hot surface interact with the surrounding plasma, scattering off charged particles and following the curvature of magnetic lines. This interaction modifies the observed spectrum, imprinting polarization and energy shifts that depend on the local field strength. In extreme regions, the magnetic field becomes so strong that it alters the very vacuum of space, making it birefringent, allowing light of different polarization states to travel at different speeds. Such quantum effects influence how the magnetar's light is seen, creating unique signatures that confirm the presence of fields beyond terrestrial limits. Within the magnetosphere, the flow of particles and fields is governed by a delicate balance between magnetic pressure, electric forces, and gravity. Though the magnetic field dominates, gravity still draws particles toward the surface, particularly near the magnetic poles where open field lines descend. Accreted matter can form thin layers of plasma, temporarily increasing the local emission. Occasionally, matter from the surrounding supernova remnant may interact with the magnetosphere, creating brief episodes of enhanced activity as it is accelerated or repelled. On rare occasions, magnetars exhibit radio pulses indicating that parts of the magnetosphere can support coherent emission, similar to that of ordinary pulsars. Such episodes often occur after X-ray flares when reconfiguration of the field changes plasma conditions. The existence of these transient radiomagnetars suggests that the boundary between magnetar and pulsar behavior is fluid, determined by the structure of the magnetosphere at any given time. Understanding this architecture provides insight not only into magnetars, but also into how magnetic fields influence plasma throughout the universe. The same principles that shape their magnetospheres operate in accretion disks around black holes and in the magnetized winds of galaxies. In each case, the interplay between rotation and magnetic tension dictates how energy flows through space. For magnetars, this interplay defines their identity, converting internal magnetic energy into observable radiation. As the magnetosphere continues to evolve, the magnetic field gradually weakens through ohmic decay and Hall drift within the crust. Over tens of thousands of years, the energy stored in twisted field lines dissipates, and the once turbulent environment grows calm. The magnetosphere becomes simpler, the bursts less frequent, the radiation softer and fainter. What remains is a quiet neutron star surrounded by the residue of its own former power, its architecture still intact but its strength diminished. Yet even in this silence, the structure persists, an invisible framework extending into space, tracing the memory of the forces that once governed it. The magnetar's magnetosphere, vast and unseen, remains the bridge between matter and energy, linking the dense interior to the wide expanse of interstellar space, a final echo of the moment when magnetic order first emerged from collapse. In the life of a magnetar, moments of violent release interrupt long periods of quiet stability. The star's magnetic field, though seemingly static from afar, stores immense tension within its twisted lines. Over time, stresses accumulate in the crust as the internal and external fields shift relative to one another. The rigid outer layer resists deformation until the magnetic pressure exceeds its breaking strength, and then it yields abruptly. When this happens, the energy of thousands of years is discharged in a fraction of a second, producing a burst of X-rays or gamma rays that travels across space. Such events are the hallmark of magnetars, distinguishing them from all other neutron stars. They come in several forms: short bursts, intermediate flares, and giant flares, each differing in duration and intensity, but sharing a common origin in magnetic reconfiguration. The smallest bursts last less than 1/10 of a second and release energy equivalent to the Sun's total output in days. They occur frequently, sometimes dozens, within a single active episode. Intermediate flares last longer, up to several seconds, and involve larger regions of the crust or magnetosphere. The rare giant flares, seen only a handful of times in recorded history, release as much energy as the Sun emits in hundreds of thousands of years. The first such event detected in 1979 saturated detectors on multiple spacecraft, demonstrating the immense power of these stars. Each flare begins with a trigger deep inside the star. As the crust fractures, magnetic field lines anchored in the solid layer snap and reconnect. This process releases a pulse of electromagnetic energy that accelerates particles in the magnetosphere and generates a flood of high-energy photons. The radiation front expands outward, briefly overwhelming any surrounding emission. In giant flares, the initial spike lasts less than a second, followed by a longer tail, modulated by the star's rotation. The periodic modulation reveals that the emission originates near the surface and is shaped by the rotating magnetic field. Observations show that after such events, the Magnetar's spin period often changes slightly, suggesting that angular momentum has been redistributed between the crust and the superfluid interior. These rotational adjustments, known as glitches, provide a window into the star's inner dynamics. Smaller bursts follow a similar but less catastrophic sequence. Magnetic stress accumulates slowly in the crust-twisting field lines that connect to the magnetosphere. When these lines reconnect, the released energy heats the surface and accelerates particles along open field lines, producing brief flashes of hard X-rays. The heated surface cools quickly, but the magnetosphere may remain energized for days or weeks, leading to extended periods of enhanced emission known as outbursts. During an outburst, the magnetar's X-ray luminosity can increase by factors of 10 or more, before gradually returning to its prior level. The decline often follows a predictable pattern, matching the expected timescale for the untwisting of magnetic field lines and the thermal relaxation of the crust. Each outburst is thus both a release and a healing process, allowing the magnetar to return to quiescence until new stresses build. Between these active intervals, magnetars remain quiet, but not inert. In their quiescent phase, they emit steady X-rays powered by the slow decay of magnetic energy. The surface temperature remains higher than that of typical neutron stars, often several million degrees Celsius, sustained by continuous internal heating. This heat leaks into space as thermal radiation, forming the soft X-ray glow detected by telescopes. The luminosity gradually declines as the magnetic field weakens, yet even after tens of thousands of years it remains detectable. These calm periods dominate most of a magnetar's lifespan. The ratio of quiet time to active time is enormous years or decades of stillness for every few seconds of bursting. Despite this apparent calm, the internal magnetic field continues to evolve. Hall drift and ohmic diffusion slowly rearrange currents within the crust, changing how the field lines thread through the star. When the rearrangement reaches a critical point, new fractures occur, restarting the cycle of activity. This pattern creates a long-term rhythm of stress and release, invisible until it manifests as a flare. Observations across decades show that magnetars are unpredictable. Some remain dormant for years, then erupt without warning. Others show repeated cycles of moderate bursts, suggesting a more stable configuration. The diversity arises from differences in field geometry, age, and internal composition. Younger magnetars, with stronger fields, tend to produce more frequent and energetic flares. Older ones whose fields have decayed exhibit longer quiescent phases and weaker outbursts. Each follows its own path of gradual cooling and magnetic relaxation. The energy released during bursts affects not only the star but also its surroundings. Flares can ionize and heat nearby gas, alter the structure of the magnetosphere, and even produce afterglows lasting days. In the most extreme cases, gamma rays from giant flares interact with Earth's upper atmosphere, temporarily disturbing radio communications and ionospheric conditions. Though these effects are minor on a planetary scale, they demonstrate the reach of these cosmic explosions across light years of distance. Within the magnetar itself, the aftermath of a burst involves both mechanical and thermal adjustments. The crust, having fractured, reseals as material shifts into a new equilibrium. The magnetic field reconfigures, reducing its twist and lowering the overall energy. The surface cools unevenly, producing hotspots that rotate in and out of view as the star spins. These hotspots create subtle variations in brightness known as pulse profiles, which change over time as the surface temperature redistributes. Monitoring these changes allows astronomers to infer the cooling rate and internal conductivity of the crust. The physics of these events connects macroscopic and microscopic scales. Crustal fractures involve the collective motion of ions and electrons in a crystalline lattice, while magnetic reconnection involves relativistic plasma and quantum electrodynamic effects. Together they form a unified process that links the star's internal structure to its observable light. Despite decades of study, the exact trigger of magnetar flares remains partly uncertain. Some models emphasize crustal breaking, others focus on instability in the external field, and some combine both. All agree, however, that the immense magnetic energy stored since the star's formation is the source. With each event, a small fraction of this reservoir is spent, gradually reducing the field and lengthening the intervals between bursts. In time, the magnetar will exhaust its ability to produce such flares, transitioning into a quieter phase resembling a typical neutron star. Until then, it continues to alternate between silence and sudden radiance, embodying both stability and change. During quiescent epochs, observers detect only steady X-rays, their regular pulsations marking rotation. Then, without warning, a flare erupts, transforming a faint point in the sky into one of the brightest sources of high-energy radiation. These contrasts between calm and chaos, darkness and light define the magnetar's existence. Yet through it all, the underlying processes remain the same: magnetic stress, crustal strain, and the relentless conversion of field energy into heat and radiation. As time passes, the intervals of activity grow longer and the bursts weaker. The magnetar enters middle age, its magnetosphere less twisted, its crust more stable. But even in this quieter state, the potential for renewal persists. The same forces that once tore the crust apart still flow beneath the surface, waiting for the next subtle shift that will release their power once again. Beneath the magnetar's glowing exterior lies a thin but immensely strong crust, only about 1 kilometer thick, yet capable of supporting pressures far beyond anything known elsewhere in nature. It forms the rigid boundary between the liquid interior and the vacuum outside, a shell of crystalline nuclei, immersed in a sea of degenerate electrons. This crust carries the imprints of the star's violent birth, and bears the strain of its restless magnetic field. Over time, it becomes a vast reservoir of tension, its structure bending and cracking under forces too subtle to measure, but powerful enough to trigger the most energetic explosions in the universe. The crust is stratified in depth. The outermost layers consist of iron nuclei compressed to densities where atoms are crushed together, forming a lattice in which electrons flow freely. As one moves inward, pressure forces electrons into protons, creating progressively neutron-rich nuclei. Eventually, neutrons begin to drip out of the nuclei, filling the spaces between them with the degenerate neutron gas. This region, called the inner crust, behaves both like a solid and a fluid, able to transmit stress yet capable of allowing matter to flow on long timescales. At its base, the density approaches that of atomic nuclei, and the distinction between individual atoms disappears. The entire layer vibrates with collective modes of motion, much like tectonic plates in slow motion, but compressed to subatomic scales. Within this crust, the magnetic field threads through the crystalline lattice in the form of flux tubes' narrow channels, where magnetic energy is concentrated. As the internal field evolves, these tubes migrate and twist, dragging against the solid lattice. The resulting shear induces strain that builds for years or centuries before reaching a breaking point. When the crust can no longer support the stress, it fractures abruptly, releasing both seismic and magnetic energy. The quake sends vibrations through the star and generates alpha waves that travel along magnetic field lines into the magnetosphere. These waves accelerate charged particles, producing X-ray and gamma-ray bursts observed from Earth. Thus, every burst witnessed from afar begins as a microscopic crack in this hidden crust. The strength of the crust depends on its composition and temperature. In young magnetars, where the surface remains extremely hot, the crust behaves more plastically, deforming gradually under stress. As the star cools, the lattice stiffens, allowing larger amounts of energy to accumulate before failure. This evolution explains why older magnetars sometimes produce the most powerful flares. Laboratory simulations using dense matter physics suggest that the breaking strain of such a crust could exceed 10 billion times that of steel. Yet even this resilience has limits under the magnetic pressures acting within a magnetar, which may reach 1,000 trillion pascals. When the field reconfigures or the internal currents shift, the crust responds with a quake that propagates across the surface in milliseconds, rearranging magnetic connections that extend thousands of kilometers outward. After each fracture, the crust settles into a new configuration. The released heat diffuses outward, creating hotspots that glow in X-rays for months or years. Observations show that after major flares, the surface brightness decays, gradually reflecting this thermal relaxation. The distribution of hotspots can also reveal the geometry of the underlying cracks. In some magnetars, the emission pattern indicates fractures along equatorial belts. In others, polar regions dominate. These differences reflect variations in magnetic topology and the direction of internal stresses. The crust also influences how the magnetar rotates. Because it is rigid, it can store angular momentum differentially from the liquid core beneath. When coupling between layers changes suddenly, perhaps due to a quake or rearrangement of magnetic flux, the crust may speed up or slow down slightly. These events are detected as glitches in the rotational timing of magnetars. Each glitch offers a rare glimpse into the interaction between the solid crust and the superfluid interior, revealing how energy and angular momentum are exchanged across the boundary. The stresses that accumulate in the crust do not act alone. They are guided by the evolution of the magnetic field anchored deep in the core. As the field decays and drifts through the crust, it exerts horizontal and vertical forces that distort the lattice. The interplay of magnetic diffusion, Hall drift, and elastic resistance creates complex patterns of motion. Regions of concentrated stress can persist for millennia, slowly deforming until conditions for rupture arise. This continuous yet unpredictable process defines the long-term activity of magnetars, a quiet struggle between rigidity and motion stability and change. The crust is also responsible for the magnetar's seismic life. When fractures occur, they excite global oscillations known as torsional modes, which cause the star to ring like a bell. During the giant flare of 2004 from the Magnetar SGR 1806-20, these oscillations were detected as quasi-periodic variations in X-ray brightness. The frequencies of these oscillations correspond to predicted crustal vibrations, confirming that seismic activity drives at least part of the observed variability. In a sense, the crust serves as both the source and the recorder of the magnetar's internal motions. Over millions of years, the crust gradually evolves as heavy nuclei sink and lighter elements float upward, a slow rearrangement known as chemical stratification. This process changes its conductivity and elasticity, influencing how the magnetic field decays. The transition between the solid crust and the fluid outer core remains one of the most mysterious boundaries in astrophysics. At this interface, magnetic flux tubes from the core anchor into the solid lattice, coupling the two regions tightly. Movement in one inevitably affects the other. When flux tubes drift or reorient, they drag on the crust, adding new stresses. When the crust cracks, the flux tubes realign, modifying the internal field. This continuous feedback links the visible activity of the magnetar to the hidden evolution of its core. Observations of long-term cooling and pulse profile variations suggest that the crust-core interaction evolves on timescales of thousands of years, slowly altering the star's emission characteristics. The crust's role extends beyond structural support. It defines how the magnetar communicates with space. The radiation we see, whether steady X-rays or sudden flares, originates in the outermost layers where magnetic energy is converted into heat and light. Even subtle shifts in crustal composition or geometry can change how this energy escapes. Some regions may act as mirrors reflecting radiation along field lines, while others absorb and re-radiate it. The interplay between crustal physics and magnetospheric dynamics determines the observable spectrum. In this way, the crust is both the barrier and the bridge between the star's interior and its cosmic surroundings. Over time, as the magnetic field decays and the crust undergoes repeated fractures, its rigidity diminishes. Microcracks and chemical changes accumulate, making it more ductile and less able to store stress. The frequency of major flares decreases and the magnetar settles into a long period of relative calm. Yet even in this quiet phase, the crust continues to bear the memory of every past event encoded in its temperature gradients and magnetic scars. Deep within, new stresses are already forming, invisible and silent, ensuring that the story of tension and release will continue as long as the magnetic field endures. Beneath the solid crust lies the outer core, a region where ordinary concepts of matter no longer apply. Here, densities exceed that of an atomic nucleus, and the immense pressure crushes atomic structure entirely. The distinction between individual atoms vanishes, leaving a continuous fluid composed mainly of neutrons, with a smaller fraction of protons, electrons, and perhaps other exotic particles. In this extreme environment, the neutrons behave collectively as a quantum superfluid, a state of matter that flows without friction, while the protons form a superconducting condensate that carries magnetic flux in quantized tubes. The coexistence of these two phases defines the internal physics of the magnetar's outer core, governing how heat, angular momentum, and magnetic energy move through the star. Within the superfluid, the neutrons align in a coherent quantum state that allows them to flow indefinitely unaffected by viscosity. This property means that when the crust rotates, the superfluid beneath does not necessarily follow in perfect synchrony. Instead, it stores angular momentum in an array of microscopic vortices, each representing a tiny quantum of rotation. These vortices can move pin and unpin against structures in the crust, leading to the sudden jumps in rotation known as glitches. The superfluid acts as a hidden reservoir of motion, coupling loosely to the crust, but capable of transferring energy when internal conditions shift. The protons, meanwhile, form a Type II superconductor, a state in which magnetic flux cannot spread evenly, but instead penetrates in discrete threads called flux tubes. Each tube carries a fixed quantum of magnetic flux, and together they form a dense lattice permeating the core. These flux tubes anchor the star's magnetic field and guide its evolution over time. They also interact with the neutron vortices, forming a complex network of microscopic forces that determine how rotation and magnetism influence each other. When vortices move, they drag flux tubes with them, altering the magnetic configuration. When flux tubes rearrange, they can change the pattern of rotation. This intimate coupling between superfluid and superconductor underlies many of the Magnetar's dynamic behaviors, linking deep internal processes to the bursts and flares observed at the surface. The motion of these structures occurs on both short and long time scales. On short scales, sudden unpinning of vortices can produce glitches, rapid changes in spin frequency. On longer scales, slow drift of flux tubes through the core drives the gradual decay of the magnetic field. The speed of this drift depends on temperature density and the strength of the coupling to the crust. In magnetars, where the internal temperature remains relatively high due to ongoing magnetic decay, these processes occur more rapidly than in older neutron stars. As a result, their magnetic fields evolve noticeably over tens of thousands of years rather than millions. The presence of superconductivity also affects how the star cools. In a normal conductor, magnetic fields dissipate through ohmic decay, generating heat. In a superconductor, such dissipation is suppressed. Instead, the energy is stored in the arrangement of flux tubes. However, when the lattice of flux tubes moves or reconnects, it releases heat that contributes to the magnetar's persistent X-ray emission. The coupling between superconductivity and superfluidity creates feedback loops. As magnetic stresses rearrange flux tubes, they influence the motion of vortices, which in turn modify rotational dynamics. These intertwined processes ensure that the magnetar's evolution remains active even in the absence of external influences. Thermal transport in the outer core is dominated by neutrinos, elusive particles that escape almost freely through the dense matter. Their production cools the core efficiently in the first 1,000 years after formation. Over time, as temperature decreases and superfluidity becomes more complete, neutrino emission weakens, allowing internal heat from magnetic decay to dominate. This interplay between cooling and heating determines the long-term surface temperature observed in X-rays. The balance is delicate. Too much cooling would freeze the crust solid and halt magnetic evolution, while too much heating would melt it. The observed temperatures of magnetars suggest that the outer core maintains a steady state, radiating energy outward at nearly the same rate it is generated within. Magnetic flux tubes being anchored deep in the core slowly migrate outward under the influence of buoyancy and tension. As they move, they interact with the crust at the boundary layer. When they reach this interface, they may break through, transferring magnetic flux into the crust and triggering the stresses that cause surface quakes. The migration of flux tubes is thought to be a major driver of magnetar activity, converting internal magnetic energy into observable events. Over thousands of years, this process reshapes the field geometry, gradually reducing its intensity, while redistributing its energy into smaller scales. The physics of the outer core cannot be observed directly, but theoretical models constrained by the behavior of magnetars provide insight. Laboratory experiments on superfluid helium and superconducting metals offer analogies, though the conditions inside a neutron star are vastly more extreme. Simulations show that the interaction between vortices and flux tubes can create turbulence, a quantum analogue of fluid turbulence seen in ordinary liquids. This turbulence could contribute to the irregular timing noise observed in magnetars reflecting microscopic motions magnified to macroscopic effects. The superconducting state also influences how the magnetar responds to rotation and precession. Because the flux tubes are anchored, any attempt to change orientation or shape must overcome their rigidity. This resistance can lead to small oscillations or wobbling of the star's rotation axis. In principle, such motion might produce gravitational waves, though the amplitude is likely too small for current detectors to measure. Still, the existence of these interactions highlights how deeply magnetism permeates every aspect of the star's structure, from quantum scales to global behavior. The outer core's superfluid nature ensures that once set in motion, internal processes continue for centuries. Angular momentum and magnetic flux migrate outward, gradually maintaining the magnetar's evolution, long after external forces have faded. The energy released by these movements sustains surface heating, keeping the star visible in X-rays even as it ages. Without the coupling between superfluid and superconducting components, the magnetar would cool and fade much more quickly. The outer core thus acts as both engine and regulator, mediating between the dense inner core and the rigid crust above. It translates microscopic rearrangements into observable phenomena, ensuring continuity between interior physics and surface activity. Over tens of thousands of years, the interactions within this layer will weaken as the field decays and temperature drops. The superfluid will become less dynamic, the superconducting lattice more stable, and the migration of flux tubes will slow. The magnetar will enter a phase of gradual quieting, its once turbulent core settling into stillness. Yet even then, the legacy of the outer core endures every glitch flare, and magnetic rearrangement recorded in the star's history begins with the silent dance of vortices and flux tubes deep within this invisible ocean of superfluid and superconducting matter. At the very center of the magnetar lies the inner core, a region so dense that no direct experimental data on Earth can reproduce its conditions. Here, matter is compressed to several times the density of atomic nuclei, and the distinction between particles begins to blur. Neutrons, protons, and electrons are squeezed together until their identities merge under the immense gravitational pressure. The inner core spans only a few kilometers in radius, yet it contains most of the star's mass. This domain represents the ultimate limit of compression before gravity would force collapse into a black hole. The physics governing it remains uncertain, existing at the boundary between nuclear and particle theory. Models suggest several possibilities for its composition, ranging from hyperon-rich matter, where strange quarks appear inside heavy baryons, to deconfined quark matter, where neutrons dissolve entirely into a fluid of free quarks. Some theories propose the presence of color superconducting phases, in which quarks pair in patterns that mimic superconductivity at the subatomic level. Others imagine a mixed state where islands of nuclear matter float within a sea of quarks. Regardless of the details, the inner core is a realm where quantum chromodynamics, the theory of strong nuclear interactions, dominates, and where even small changes in density or pressure can alter the entire state of matter. The transition from the outer to inner core is gradual rather than sharp. As one moves inward, neutron degeneracy pressure increases until it can no longer support the weight of the overlying layers. New particle species appear to relieve the pressure. Muons, hyperons, and eventually strange quarks emerge as the energy of the system rises. Each new component affects the star's stiffness, the equation of state that determines how much mass it can hold before collapsing further. A stiffer equation of state allows a larger, more stable neutron star. A softer one brings it closer to the threshold of a black hole. Observations of magnetar masses suggest that they exist near this boundary, heavy enough to require exotic matter, but still light enough to resist total collapse. Within this core, the same interplay between magnetism and quantum structure continues, but on even more extreme terms. The magnetic field permeates the matter, modifying particle motion and energy levels. Electrons spiral along magnetic lines at nearly the speed of light, while quarks experience altered confinement due to the field's strength. The magnetic pressure may even change the geometry of the core, flattening it slightly along the magnetic axis. The field anchored deep within interacts with the superconducting protons of the outer core, transmitting tension outward and ensuring that the magnetar's immense surface magnetism remains tied to its hidden heart. Energy transport in the inner core is dominated by neutrinos, which can escape only slowly through the dense material. The rate of neutrino emission depends on the types of particles present. If quark matter exists, it may allow more efficient cooling through direct Urca processes, rapid reactions converting neutrons to protons and back with neutrino emission. If the core remains purely nucleonic, cooling proceeds more gradually through modified processes. These differences determine the long-term temperature evolution of the magnetar and may explain why some magnetars cool faster than others despite similar ages. The presence of superfluid or superconducting phases further complicates the picture. In such states, certain reactions are suppressed, delaying cooling and preserving heat for longer periods. Thus, the thermal history of a magnetar encodes information about its deepest interior. Because no direct observation can probe these depths, astronomers rely on surface emission rotation and magnetic decay to infer what lies within. Computer simulations attempt to model the equation of state by fitting these macroscopic properties. The results point toward a dense but compressible core that resists total collapse while supporting the strong external field. In the earliest moments after formation, the inner core is still dynamic. Shock waves from the supernova bounce through it, and neutrino fluxes reshape its pressure balance. Within seconds, the system stabilizes into hydrostatic equilibrium, where the inward pull of gravity balances the combined pressures of nuclear forces, degeneracy, and possibly quark interactions. Over thousands of years, the composition evolves as particles rearrange into lower energy configurations. This slow transformation releases or absorbs energy, depending on the phase transitions involved. If quark matter appears, gradually latent heat can influence the cooling curve, producing subtle changes in luminosity detectable in X-ray observations. Some theoretical models suggest that magnetars might represent the visible stage of such internal transitions. The extreme magnetic field could favor deconfined matter by altering the motion of charged particles and reducing their effective masses. If this occurs, the magnetar's inner core may become a quark-hadron hybrid, with the outer layers still neutron-rich and the center a dense quark fluid. In these conditions, magnetic and rotational instabilities could trigger additional bursts or affect long-term stability. Though speculative, this idea illustrates how tightly the magnetar's observed properties are linked to physics far beyond the reach of terrestrial experiments. The gravitational field in the inner core is immense. A difference of 1 centimeter in radius corresponds to a change in gravitational potential larger than that between Earth's surface and orbit. Such gradients compress the matter into nearly perfect spherical symmetry, yet the magnetic field breaks this symmetry slightly, introducing anisotropy in pressure. These differences may produce quadrupole deformations, potential sources of continuous gravitational radiation. The strength of such emission remains uncertain, but if detectable, it would provide a direct probe of the star's interior. For now, indirect evidence comes from the stability of rotation and the energies of observed flares, both consistent with enormous internal magnetic tension. The microphysics of the inner core also governs how the magnetar approaches its final state. As the magnetic field decays, the loss of internal support may shift pressure balances, leading to contraction, or even delayed collapse if the mass exceeds a critical threshold. In this scenario, a magnetar could end its life not through explosion but through silent implosion into a black hole, its magnetic field disappearing as the event horizon forms. Whether this happens in nature is unknown, though theoretical models suggest it could explain certain fast luminous transients seen in distant galaxies. If so, the death of a magnetar would mark the boundary where matter, magnetism and light all surrender to gravity. Despite such possibilities, most magnetars remain stable for hundreds of thousands of years. Their inner cores, though dense beyond comprehension, endure as static reservoirs of pressure and energy. Within these few cubic kilometers lie the conditions that define the behavior of the entire star. Every surface burst, every rotational glitch, every subtle pulse of X-rays traces its origin back to this unseen region. It is the foundation upon which all other layers rest, the ultimate engine of the magnetar's existence. Even when the outer field fades and the surface cools, the core remains intact, its exotic matter locked in equilibrium. The physics here is inaccessible, yet through the quiet light of distant magnetars, humanity glimpses hints of what occurs when matter is pushed to its final limits, where the building blocks of atoms dissolve and the universe's most fundamental forces reach balance under gravity's unrelenting hand. Every magnetar spins, and in its rotation lies a chronicle of its internal dynamics and magnetic history. When newly born, the star can rotate many times per second, its angular momentum inherited from the progenitor's collapsing core. But magnetic braking, the gradual transfer of rotational energy into the magnetosphere, slows it dramatically over time. Within only a few thousand years, the period lengthens to several seconds, making magnetars among the slowest spinning neutron stars known. This deceleration is steady on long scales, but punctuated by irregular events, sudden speed-ups or changes in timing called glitches, that reveal interactions between the crust and the superfluid interior. Each glitch is a window into the hidden workings of the star, linking its rotation to processes of stress motion and magnetic evolution deep inside. The braking mechanism that governs long-term slowing arises from electromagnetic torque. As the star's magnetic field co-rotates with it, it induces electric currents in the surrounding plasma, creating a flow of charged particles that carry angular momentum outward. This continuous emission of energy powers the magnetosphere and gradually robs the star of spin. The rate of loss depends on magnetic field strength angle between the magnetic and rotational axes and the density of plasma in the surrounding space. For magnetars with fields 1,000 times stronger than those of ordinary pulsars, this braking is intense. Over 10,000 years, they can lose more than 90% of their initial rotational energy. The energy extracted in this process appears as X-ray and gamma-ray emission, providing the persistent glow observed even in quiet phases. Yet the deceleration is not perfectly smooth. Timing observations show abrupt jumps in rotation, frequency glitches that occur unpredictably. These events are understood as the sudden unpinning of quantized vortices in the superfluid outer core. As the crust slows due to magnetic torque, the superfluid beneath retains its angular momentum. The vortices pinned to lattice sites in the crust accumulate stress until they break free, transferring stored angular momentum to the outer layers. The result is a measurable increase in spin rate, sometimes followed by a gradual relaxation as the system re-equilibrates. Each glitch therefore represents an internal realignment between crust and core. The size and frequency of these events vary widely. Some magnetars show small frequent glitches, others display rare but large ones accompanied by X-ray bursts, suggesting a coupling between mechanical and magnetic processes. The simultaneous occurrence of rotational changes and radiative outbursts implies that when the crust cracks, or magnetic flux moves, both angular momentum and magnetic energy are redistributed. In the aftermath of a glitch, the star's spin-down rate often changes temporarily, indicating a shift in torque or internal coupling. Over years, the rate returns to its prior value, but the cumulative effect is a slow decline toward longer periods. This interplay of steady braking and intermittent adjustment gives magnetars their distinctive rotational behavior, regular enough to serve as cosmic clocks, yet irregular enough to reveal the turbulence beneath their calm surface. Long-term evolution extends beyond rotation alone. As the magnetic field decays, the braking torque weakens and the magnetar's period stabilizes. Over tens of thousands of years, the field strength may decrease by an order of magnitude, reducing both luminosity and variability. The decay itself arises from several physical processes: ohmic dissipation, where electric currents in the crust convert magnetic energy into heat; Hall drift, where currents interact with magnetic fields and move them through the crust; and ambipolar diffusion, where charged and neutral particles drift relative to each other in the core. Together, these mechanisms redistribute and gradually dissipate magnetic energy, turning it into thermal radiation, observable at the surface. During this stage, the magnetar cools slowly, but remains warmer than non-magnetic neutron stars of the same age. The balance between field decay and cooling sets the pace of evolution. In the earliest 1,000 years, when magnetic energy is abundant, decay dominates and keeps the star luminous in X-rays. Later, as the field weakens, heat escapes faster than it can be replenished. The surface temperature declines and the emission softens into ultraviolet and then invisible infrared. The once dramatic bursts become rare, replaced by steady, faint pulsations. Eventually, the magnetar's outer field becomes indistinguishable from that of an ordinary neutron star, though internally, its magnetic configuration may remain strong but buried. Glitches persist throughout this aging process, though they become less frequent and less intense. The internal superfluid, now cooler and less mobile, stores smaller amounts of differential rotation. The crust, having endured countless fractures, grows more plastic, accommodating stress without sudden breaks. Still, each occasional glitch continues to remind astronomers that the connection between deep interior and outer layers remains active even in old age. Observations of different magnetars show that rotation and magnetic decay proceed in tandem. Young, rapidly spinning magnetars exhibit frequent bursts and erratic timing, while older, slower ones emit steady light and show stable periods. The relationship between spin period-period derivative and magnetic field, known as the PP diagram, places magnetars at one extreme of neutron star behavior, distinct from both radio pulsars and accreting X-ray binaries. This diagram tells the story of their entire life cycle, from energetic youth through gradual decay toward quiescence. The long-term fate of a magnetar depends on its initial conditions. Those born with exceptionally strong fields may lose so much rotational energy that they slow to a near standstill, their emissions fading below detection thresholds. Others with slightly weaker fields may persist as dim X-ray pulsars for hundreds of thousands of years. A few may undergo structural changes that transform them into more conventional neutron stars as their magnetic fields reorganize and decay. Some theories propose that even after apparent quiescence, residual magnetism may persist deep hidden beneath the surface for millions of years, influencing how the star interacts with its environment. Over cosmic timescales, Rotation and magnetism act as dual chronometers recording the magnetar's passage from formation to extinction. Each spin, each flare, and each interval of quiet adds another mark to this timeline. The smooth deceleration traces the slow expenditure of energy, while the glitches and bursts record the sudden, unpredictable adjustments of a complex internal system seeking balance. Though Magnetars eventually fade from view, their contributions to the galactic environment endure magnetic fields dispersed through space-heavy elements from their supernova and perhaps even gravitational waves from their early oscillations. The study of their rotation provides more than a description of stellar mechanics. It offers a measure of time itself on scales far exceeding human experience. In the near-perfect regularity of their pulses, and the rare moments when that regularity falters, Magnetars reveal the intimate link between order and disruption that governs the universe's most extreme objects. Over thousands of years, each one follows a slow trajectory from fire to quiet light, from rapid spin to stillness. The rhythm of rotation, once furious, becomes gentle. The magnetic storms that once shaped the sky settle into calm. In the end, the Magnetar persists as a monument of endurance, its heartbeat measured not in seconds, but in the slow turning of an invisible clock whose hands are fields, currents, and the endless dialogue between gravity and magnetism. From the moment of its birth, a Magnetar begins an extended process of cooling, a gradual release of the enormous heat generated during its formation and sustained by its decaying magnetic field. In the first seconds after collapse, the internal temperature reaches over 1 trillion degrees Celsius. At that level, thermal energy dominates every motion within the dense matter, and the star emits a torrent of neutrinos, nearly massless particles that escape freely carrying energy away. Within minutes, the temperature drops by a factor of 100. Over the next 1,000 years, this cooling continues governed by the complex interplay between heat production in the core and energy loss through radiation and neutrino emission. The Magnetar's unique internal structure, its superfluid neutrons, superconducting protons, and evolving magnetic field, determines how quickly it cools and how its thermal energy flows from the interior to the surface. In the earliest phase, neutrino emission dominates. These particles, produced through weak nuclear reactions among the densely packed baryons, are far more efficient at removing heat than photons. They travel through the opaque matter, almost unhindered, escaping into space and carrying the bulk of the star's thermal energy. This rapid loss continues until the temperature falls below about 10 billion degrees Celsius, when neutrino production rates decline sharply. As the star cools, the outer layers solidify, forming the crust that insulates the interior. The thermal gradient between core and surface steepens, and heat begins to move outward through conduction. At this point, the surface temperature stabilizes at several million degrees Celsius, still bright in X-rays but far lower than the inferno of formation. Even as neutrino cooling wanes, the Magnetar's strong magnetic field introduces new complexity. The field affects how electrons move through the crust, aligning their trajectories along magnetic lines and suppressing motion across them. This anisotropy alters thermal conductivity, making heat flow more efficiently toward the magnetic poles than the equator. The result is an uneven surface temperature. The poles glow hotter, while the equatorial regions remain cooler. Observations of Magnetar X-ray light curves confirm this pattern, showing pulsations caused by hotspots rotating in and out of view. These temperature variations also evolve over time, responding to the slow decay and rearrangement of magnetic fields within the crust. As the field relaxes, magnetic energy converts into heat, partially offsetting the cooling. This internal heating extends the Magnetar's thermal lifetime far beyond that of ordinary neutron stars, While a typical neutron star might fade to invisibility after 1,000,000 years, a magnetar can remain detectable for several million years due to this steady replenishment of surface heat. The balance between heating and cooling defines its thermal evolution, a dynamic equilibrium between loss and renewal. Deep in the core, superfluidity and superconductivity influence both heat capacity and neutrino production. When neutrons pair into a superfluid, their ability to emit neutrinos changes dramatically. The pairing process itself can release bursts of neutrinos, but once established, the superfluid suppresses further emission. Similarly, superconducting protons alter the behavior of charged particles, modifying how heat diffuses and how magnetic fields evolve. These microphysical effects regulate the core's temperature, ensuring a smooth decline rather than a sudden collapse of thermal energy. Because direct observation of the core is impossible, astronomers infer these processes by measuring how the surface temperature changes with age. The cooling curve, a plot of temperature versus time, serves as a fingerprint of the star's internal composition. Magnetars, with their strong fields and continuing magnetic decay, show slower cooling than predicted for ordinary neutron stars, confirming that magnetic heating plays a major role. The crust itself acts as both conduit and regulator. Its conductivity depends on composition impurity content and the presence of nuclear pasta complex structures of nuclei that form near the base of the crust under immense pressure. These irregular shapes can scatter electrons and impede heat flow, altering the thermal profile. Regions of high impurity retain heat longer, while purer regions cool faster. The interplay between these microscopic details and global magnetic structure creates a patchwork of temperature variations across the surface. Over thousands of years, these differences smooth out as conduction redistributes energy, but after every burst or quake, new asymmetries appear, producing the transient hotspots observed after magnetar flares. Above the crust, a thin atmosphere of ionized particles radiates energy into space. The spectrum of this radiation depends on surface composition and magnetic field strength. In strong fields, atoms elongate and bind more tightly, affecting how they emit and absorb photons. The resulting X-ray spectra deviate from simple blackbody curves, requiring complex models to interpret. Polarization measurements of this light reveal additional details. Photons escaping through magnetized plasma exhibit distinct polarization angles, offering a diagnostic of surface field strength and geometry. These subtle clues allow astronomers to reconstruct how heat escapes from regions invisible to direct observation. The cooling of a magnetar also influences its timing behavior. As temperature drops, superfluid regions expand, changing the coupling between crust and core. This can modify glitch frequencies and the rate of spin down. In older magnetars, where the interior has cooled substantially, these adjustments occur less often, contributing to the stability observed in their later evolution. At the same time as temperature declines, magnetic diffusion slows, reducing internal heating and accelerating the final fade toward quiescence. The transition from active magnetar to quiet neutron star occurs gradually, with the surface temperature dropping below 1,000,000 degrees Celsius and the emission shifting from X-ray to ultraviolet. Even then, residual magnetic decay continues to release small amounts of heat, keeping the star slightly warmer than its non-magnetic counterparts. This lingering warmth marks the final phase of thermal balance, a quiet equilibrium maintained between the last vestiges of magnetic energy and the unrelenting loss of heat to space. Cooling does not proceed in isolation. The magnetar's environment responds to its thermal evolution. As the surface radiation weakens, the surrounding supernova remnant dims, and dust cooled by earlier outbursts fades into the background. Over tens of thousands of years, the region around the Magnetar merges indistinguishably, with the interstellar medium leaving the star alone in the vast galactic field. Yet even as its light grows faint, the internal processes that once powered bursts and flares persist at microscopic scales. The balance of heating and cooling continues until magnetic energy is exhausted and neutrino emission ceases. What remains is a cold, dense sphere still bound by gravity, its internal motion nearly frozen, its magnetic field a fossil of earlier strength. The path to this final state is long, and measured a slow dimming rather than a sudden extinguishing. In the universe's quiet clockwork, the magnetar cools with steady precision, its fading heat radiating through the dark as one of the last traces of energy born from a massive star's collapse. In its dwindling light lies a record of every process it has endured, the furious birth, the magnetic storms, the quakes and flares, and the gradual surrender to stillness. The cooling curve that astronomers trace from afar is not merely a graph of temperature. It is the slow heartbeat of the cosmos written in thermal decay. Within the Milky Way, Magnetars are rare jewels hidden among hundreds of millions of ordinary stars. Only a few dozen have been identified, their positions scattered along the plane of the galaxy, where massive stars are born and die. This sparse population reflects the conditions required for their creation: immense progenitor mass, rapid rotation at collapse, and magnetic field amplification during formation. Each known magnetar occupies a different stage of its evolution, allowing astronomers to piece together a timeline of birth activity and decay. Taken together, they form a small but vital subset of neutron stars that illuminate the extreme physics of matter and magnetism. Their distribution traces the spiral arms following the regions richest in young high-mass stars. These areas, known as star-forming complexes, host clusters filled with O and B-type stars, many of which will one day explode as supernovae. Magnetars, being short-lived on cosmic timescales, seldom drift far from their birthplaces. Their characteristic ages derive from rotation period, and its rate of change range from a few thousand to about 100,000 years, a mere instant in galactic history. Because they are young, they often remain embedded within or near supernova remnants, glowing shells of ionized gas that mark their violent origin. Observations across the electromagnetic spectrum reveal these remnants as circular or irregular structures, a few dozen light-years across, still expanding into surrounding space. Some magnetars reside within well-defined remnants, whose shapes and compositions provide clues to their progenitors' mass and energy. Others stand alone, their remnants dispersed or too faint to detect. The proximity of magnetars to massive star clusters further confirms their youthful nature. Infrared surveys frequently reveal nearby associations of hot luminous stars, suggesting that these neutron stars were born from the same molecular clouds. Statistical studies estimate that roughly 1 in 10 neutron stars may form as a magnetar, though only a fraction are active at any given time. Many may pass through a magnetar-like phase early in their lives, before evolving into quieter neutron stars or ordinary pulsars as their magnetic fields decay. Thus, the observed population likely represents only the visible tip of a much larger and more transient class of objects. The discovery and study of magnetars rely heavily on X-ray and gamma-ray observatories. Because their emissions are mostly high energy, they are invisible to optical telescopes except during rare flares. Instruments such as Fermi Swift and Nike monitor the sky for transient events, flagging bursts that mark the location of these compact stars. Once identified, follow-up observations measure their spin luminosity and spectra. These data populate a growing catalogue of magnetars, each entry contributing to a clearer understanding of their demographics. Despite their small number, magnetars exert a significant influence on the galaxy's energetic landscape. Their bursts and flares inject high-energy particles and magnetic disturbances into the interstellar medium. Over time, this input may help sustain the large-scale magnetic field permeating the Milky Way. In addition, the heavy elements dispersed by their progenitor supernovae enrich nearby gas clouds, seeding future generations of stars and planets. The feedback loop between magnetar formation and galactic evolution extends far beyond the lifetime of any single object. Comparisons with other galaxies show that magnetars are not unique to the Milky Way. Similar sources have been detected in the Large and Small Magellanic Clouds and in more distant galaxies observed through their giant flares. These extragalactic magnetars demonstrate that the same physical processes operate universally wherever massive stars form. In galaxies with high star formation rates such as starbursts, magnetars may be more common, their frequent births fueling a constant cycle of high-energy activity. In contrast, older quiescent galaxies produce fewer massive stars and thus host fewer magnetars, showing how stellar demographics shape the cosmic distribution of extreme objects. Within the local galaxy, magnetars often appear in environments already shaped by previous generations of massive stars. Expanding supernova bubbles overlap, forming cavities filled with hot rarefied gas. Magnetars born in these regions interact with pre-existing magnetic structures, sometimes aligning with large-scale fields and sometimes distorting them. Over time, their outbursts contribute to the turbulence and heating of the interstellar medium. Even though individual events are rare, their cumulative energy input across millions of years is substantial. The population's spatial pattern also carries information about stellar migration and galactic structure. Because the Milky Way's spiral arms rotate at different speeds than its stars, magnetars observed today trace a slightly shifted version of the arms in which they were born. This drift provides clues to the dynamics of the disk and to the history of star formation across galactic time. By mapping their positions and ages, astronomers reconstruct the regions where massive stars have recently died, linking magnetar populations to broader patterns of stellar evolution. The study of magnetars also intersects with research on fast radio bursts, brief intense flashes of radio waves originating far beyond the Milky Way. Several models suggest that young magnetars may be the engines behind these mysterious signals, releasing energy through magnetic reconnection or crustal fractures that send coherent radio pulses across intergalactic space. Observations of fast radio bursts repeating from the same source strengthen this link, as some known magnetars have exhibited similar behavior during outbursts. If confirmed, this connection would extend the relevance of magnetars from local astrophysics to cosmological distances, making them beacons for studying the universe's large-scale structure. Population studies indicate a diversity of behaviors even among magnetars of similar age and magnetic field strength. Some remain persistently bright, their X-ray flux stable over decades, while others alternate between long dormancy and sudden flaring. The reasons for these differences likely lie in the geometry of their magnetic fields and the conductivity of their crusts. Multipolar components regions of complex magnetic structure can concentrate stress locally, producing more frequent bursts. Simpler dipolar fields may decay more smoothly, leading to quieter evolution. In this way, magnetars exhibit individuality despite sharing a common origin. Understanding their variety helps refine models of magnetic field generation and decay in neutron stars. Over time, as more are discovered, patterns emerge. Younger magnetars cluster near the galactic center, and inner spiral arms where star formation is most vigorous. Older, fainter ones spread outward, marking the gradual diffusion of remnants from earlier epochs. Together they form a loose chronicle of the galaxy's activity, tracing where massive stars once lived and how their deaths continue to shape the environment. The Magnetar population, though small, represents an essential link between stellar evolution and galactic ecology. Each object encapsulates an entire sequence of physical extremes from fusion and collapse to magnetism and radiation, and their combined influence echoes far beyond their short active lifetimes. When viewed on a galactic scale, they appear as momentary sparks, brief in duration, yet essential to the long balance of matter and energy that defines the Milky Way. Long after their light fades, the fields they released and the elements they scattered persist, woven into the next generation of stars. In this quiet continuity, the rare Magnetar becomes both relic and architect, shaping the galaxy that gave it birth. Over thousands of years, the Magnetar's fierce energy softens into quiet persistence. Its rotation slows to only a few turns per minute, its surface cools to a faint glow, and its bursts fade to silence. Yet even in this subdued state, it remains one of the most extreme objects in existence, a monument to forces that still defy full understanding. The end of a magnetar's active life is not abrupt but gradual, a slow transformation from a dynamic magnetically powered star to a quiescent neutron star indistinguishable from countless others. The processes that drive this change, magnetic decay, thermal diffusion, and mechanical relaxation, occur over tens or hundreds of thousands of years, gradually draining the stored energy that once fueled flares and heat. As the external magnetic field weakens, the crust becomes less stressed, the magnetosphere relaxes and the periods of stillness grow longer. Eventually, the surface temperature falls below 1 million degrees Celsius, and the emission shifts from X-rays to ultraviolet light, then to faint optical wavelengths, before disappearing entirely from human instruments. Inside, however, the story continues. The decay of the magnetic field does not stop when the external field becomes undetectable. Deep in the core, superconducting currents persist, slowly dissipating through quantum processes that may last millions of years. The field, though weakened, remains frozen into the structure of the star. Some models suggest that residual magnetism could survive indefinitely, turning the Magnetar into a dormant neutron star with a quiet but enduring magnetic heart. Others propose that the field eventually reorganizes itself, emerging again as a weaker dipole, giving the star a second, more subdued phase of electromagnetic activity. These transitions remain theoretical, as no Magnetar has yet been observed to complete its life cycle. Another possibility lies at the extreme end of mass and density. If a Magnetar's mass exceeds a critical threshold, or if its magnetic energy supports it against collapse for only a limited time, the decay of the field could remove that support and trigger gravitational instability. In that case, the star would implode into a black hole, its magnetic field vanishing beyond the event horizon. Some short-lived high-energy transients observed in distant galaxies may represent this final transformation, a Magnetar collapsing silently, releasing a last flash of energy as it disappears. Whether such collapses occur naturally remains uncertain, but they mark one of the frontiers of astrophysical theory. Even if collapse does not happen, the final stages of Magnetar evolution remain filled with unanswered questions. How long can the internal field persist before dissipating entirely? What precise combination of decay, rotation, and temperature determines the transition to quietness? How do differences in field geometry or initial mass influence the outcome? Observations provide only partial answers, and theoretical models diverge depending on assumptions about the behavior of matter at nuclear densities. Despite decades of study, no single equation of state has yet explained all neutron star phenomena simultaneously. The Magnetar sitting at the far edge of parameter space tests every theory to its limit. As astronomers look beyond the Milky Way, they continue to discover signs that magnetars may play roles far grander than once imagined. The repeating fast radio bursts detected across the universe, millisecond flashes of intense radio energy, appear in some cases to originate from young, highly magnetized neutron stars. Their energy output, though brief, rivals that of entire galaxies for an instant. If magnetars indeed produce these events, they serve as lighthouses visible across billions of light years, connecting stellar physics to cosmology. This realization redefines magnetars not merely as remnants of stellar death, but as engines of intergalactic communication, sending out signals shaped by magnetic reconnection or crustal cracking on a scale impossible to duplicate on Earth. Closer to home, magnetars also help scientists understand the magnetic history of galaxies. Their cumulative outflows of charged particles contribute to the diffuse cosmic background and influence how interstellar gas evolves. The heavy elements dispersed by their progenitors form the building blocks of planets and life. Thus, each magnetar's death enriches the cosmos, its energy, and matter absorbed into the ongoing cycle of creation. Even after the magnetar becomes too cold to detect directly, its legacy persists in the galactic magnetic field and the chemical composition of future stars. The study of these objects continues to evolve as technology advances. Future X-ray and gamma-ray telescopes will reveal finer details of their bursts and cooling curves. Gravitational wave observatories may one day detect ripples from their crustal oscillations, or late-stage contractions, providing a new way to probe their interiors. Radio arrays already monitor the sky for signals that might mark magnetar births, tracing the aftermath of recent supernovae. Each new detection refines our understanding of how often these stars form, how long they remain active, and how they finally fade. Yet despite all progress, mysteries endure. The origin of their magnetic fields remains incompletely understood, whether they arise purely from dynamo amplification in the proto-neutron star or from fossil fields inherited from their progenitors. The link between magnetar flares and fast radio bursts remains tentative, awaiting further simultaneous detections. The ultimate limit of magnetic field strength in nature is still an open question. Even the precise mechanism of burst generation, whether it begins in the crust, the magnetosphere, or both, has yet to be resolved. Magnetars stand as both evidence and challenge proof that the universe can create stable objects at the edge of physical possibility, and a reminder that human comprehension of matter and energy is still incomplete. Their study bridges disciplines nuclear physics, quantum mechanics, plasma dynamics, and relativity, each necessary to describe different layers of the same object. The persistence of unknowns ensures that magnetars remain a focus of fascination long after the last of their light has faded. In the far future, long after their surrounding remnants have dispersed, the magnetars themselves will endure as silent fossils of cosmic power. Their magnetic fields, though decayed, will still trace delicate arcs through the interstellar medium. Their dense matter will remain stable for billions of years unless disturbed by collision or accretion. A traveller passing one of these extinct stars would find no visible sign of its past violence, only a sphere of dense matter turning slowly in the dark, colder than the space around it, yet still bearing the imprint of its magnetic ancestry in the alignment of surrounding dust and plasma. The end of a magnetar is not an event but an absorption into the wider universe, a quiet merging with the environment it once transformed. It is the final balance point in a continuum that began with stellar birth and nuclear fire passed through collapse and explosion and settled into magnetic stillness. Its fading marks not disappearance, but completion. In its silence, the Magnetar embodies the full arc of cosmic evolution, from the brilliance of creation to the equilibrium of decay, its existence both fleeting and eternal within the fabric of the galaxy.